In this paper, we propose a deep metric learning approach to unifying mesh saliency and non-rigid shape matching. Human annotate saliency typically identifies the thematically important surface points which are consistent within a shape category. Shape matching also aims at finding thematically meaningful points correspondence across shapes. It therefore should preserve the distribution of salient points within a shape category. Previous work tackled saliency detection and shape matching separately, leaving the gap that saliency lacks consistency and shape matching lacks saliency. We bridge this gap by unifying the learning and inference of saliency and matching using a metric representation. This allows matching to improve the intra-category consistency of saliency, and also allows saliency to provide thematic feature localization for matching. Our contributions include a unified metric model of saliency and matching, as well as a general and powerful deep metric representation. Here, we give an overview of our proposed method. For each point on a mesh, we first extract a set of raw multiscale features, which combine local and global shape contexts. We then fit the features into a set of recurrent neural networks, which effectively transform low-level geometric features for the subsequent metric computation. In order to generate a metric for each scale, we compute a matrix of squared Euclidean distance among all points from the RNN's output. We then pull across these multiscale distance matrices to obtain a scale-free metric of sufficient representation capacity. Finally, since the ground truth saliency is sparse, we apply soft thresholding to obtain a sparse metric. We use its principal eigenvector and Laplacian eigenvectors for saliency detection and shape matching respectively. We train our system by jointly minimizing the saliency fitting loss, saliency consistency loss, and metric consistency loss on the ground truth saliency and shape matching databases. Here, we demonstrate how saliency and shape matching benefits each other. From left to right, we show our system saliency testing error, saliency consistency error, and the metric consistency error. We use 4 colors to represent 4 setups of loss terms. Minimizing the 3 losses together produces the lowest errors. Here, we show our compute saliency maps with and without matching. We can see that with matching, the salient points are more sharply highlighted. When matching is incorporated, the salient points are more robust against shape deformations. Now, we show the first 7 dimensions of the embeddings to be used for shape matching. The upper one is the Laplacian spectral embeddings, and the lower one is our saliency-induced embeddings. Our embeddings at the bottom localize salient points very sharply and achieve maximum invariance for non-salient points. Here, the black point on each shape is considered as a reference point. The reference points of the left-hand side shapes are located at the salient points, and that of the right-hand side shapes are at non-salient points. Blue color visualize short distance to a reference point, and red color visualize long distances. Our embeddings at the bottom localize salient points very sharply and achieve maximum invariance for non-salient points. Here, we show our compute shape correspondence with and without saliency. Saliency reduces the shape matching error at the back of the human body shape. When saliency information is incorporated, our compute correspondences are more accurate under complex deformations of clothings.